In the darkness beyond all that we have ever seen, something has been waiting. If you can, watch this in full screen. And if this journey moves you, subscribe to follow where the evidence leads. Because what the James Webb Space Telescope has revealed is not simply a collection of distant objects, but a vast, interconnected architecture of galaxies that extends far behind the boundaries of what we once called the known universe. A structure so immense and so organized that it demands we reconsider not only the map of existence we have drawn, but the very assumptions upon which that map was built. For generations, human beings have looked upward and outward, reaching with instruments of ever-increasing power toward the edge of visibility, constructing from light and mathematics a picture of the cosmos that seemed, if not complete, then at least coherent within its own borders. We identified galaxies by the billions, traced the expansion of space itself back toward an origin point some 13.8 billion years in the past, and established through painstaking observation the fundamental architecture of large-scale structure. Superclusters, voids, filaments, a cosmic web woven from gravity and dark matter across distances that beggar comprehension. Yet all of this, vast as it seemed, was contained within a sphere defined not by physical boundaries, but by the limits of our technology, the sensitivity of our instruments, and the assumptions we made about what lay beyond the furthest light we could detect. And now, with the deployment of an observatory designed to see in wavelengths that previous generations of telescopes could barely touch, those assumptions have been shattered, replaced by something stranger and more intricate than the models predicted. The James Webb Space Telescope, positioned far from Earth at a gravitational balance point where the pull of our planet and the sun cancel into stillness, was engineered specifically to capture infrared radiation, light stretched by the expansion of the universe into wavelengths too long for human eyes, too red for the Hubble Space Telescope to perceive with clarity. This was not a peripheral capability, an afterthought added to a broader mission, but the central purpose of the machine: to look deeper into time and space than any instrument before it, to see galaxies not as they are now, but as they were billions of years ago, when the universe was young and light from those distant places was only beginning its long journey toward us. Infrared observation allows this because as space itself expands, it stretches the light traveling through it, shifting photons that left ancient stars as visible or ultraviolet radiation down into the infrared spectrum by the time they reach our corner of the cosmos. The further away an object is, the more extreme this redshift becomes, until visible light is stretched so far that only infrared detectors can register it at all. Hubble, magnificent though it was, operated primarily in the visible and near-ultraviolet ranges. It could see far, but not far enough. It could look back to galaxies formed a billion years after the Big Bang. But beyond that, a veil of insufficient sensitivity fell across the cosmos, leaving an entire epoch of galactic history invisible, inferred but not observed. James Webb was built to tear that veil away. Its mirror, a hexagonal mosaic of gold-coated beryllium segments nearly 6.5 meters across, collects light with a surface area far greater than Hubble's, and its instruments are cooled to temperatures barely above absolute zero to prevent their own heat from drowning out the faint infrared whispers arriving from the edge of observable space. When it began returning data, the scientific community expected breakthroughs. They expected to see the first galaxies in greater detail, to refine models of early star formation, to probe the atmospheres of exoplanets with unprecedented precision. What they did not expect, what no model, no simulation, no theoretical framework had fully anticipated, was the discovery of a coherent, organized web of galaxies occupying regions of space that prior surveys had cataloged as empty or sparsely populated, a hidden architecture extending behind and beyond the structures we had already mapped, connected by filaments of matter that suggested not random chance, but a deeper order, a pattern woven into the fabric of the universe from times and distances we had believed to be beyond our reach. The first hints appeared in what were intended to be calibration images, test exposures taken to verify that the telescope systems were functioning as designed. The fields chosen for these tests were not empty, but they were known, patches of sky that Hubble and other observatories had already surveyed, areas where the density and distribution of galaxies had been cataloged and considered well understood. Yet when Webb turned its gaze upon these same regions, the images that emerged were crowded with objects that had never been seen before. Galaxies, hundreds of them, thousands of them, filling spaces that previous observations had recorded as voids. At first, there was caution. Any new instrument reveals details missed by its predecessors. Increased sensitivity naturally uncovers fainter sources. But as the data accumulated and the redshifts of these newfound galaxies were measured, redshifts indicating distances so extreme that the light now reaching us had been traveling for more than 13 billion years, it became clear that this was not merely a matter of enhanced resolution. These were not simply more distant examples of the same structures we had already cataloged. These galaxies were organized. They formed filaments, walls, clusters, a continuation of the cosmic web that did not fade into randomness at the edges of previous surveys, but instead extended, coherent, and structured, into regions of space that have been assumed to mark the practical boundary of detailed observation. Understanding what this means requires returning to the very foundation of how we measure distance and time in the universe, to the fundamental relationship between light, expansion, and observation that governs all of cosmology. When we look at a distant galaxy, we're not seeing it as it is now, in whatever present moment might be said to exist across the vast separation between us. We are seeing it as it was when the light now entering our telescopes first left its stars, and because light travels at a finite speed, approximately 300,000 kilometers per second, the further away an object is, the further back in time we are observing. A galaxy 1 million light-years distant is seen as it was 1 million years ago. A galaxy 1 billion light-years away appears to us as it existed 1 billion years in the past. This delay is not a limitation to be corrected, but a fundamental feature of observation in a relativistic universe. And it transforms every telescope into a time machine. Each deeper survey, a journey not merely outward, but backward, toward the origin of everything. But distance and look-back time are complicated by the fact that space itself is expanding. The universe is not a static container within which galaxies move. It is a dynamic fabric that stretches, carrying galaxies along with it, increasing the separation between them without requiring that they move through space in the conventional sense. This expansion has profound consequences for light traveling across cosmological distances. As space stretches, so too do the wavelengths of photons traversing it, shifting their light toward the red end of the spectrum. A phenomenon called cosmological redshift, distinct from the Doppler shifts caused by objects moving through space, though the two effects are often conflated in popular discussion. The amount of redshift encodes information about how much the universe has expanded since the light was emitted, which in turn reveals how long ago that emission occurred and how far away the source is now, accounting for the expansion that has happened in the interim. Galaxies with higher redshifts are further away and seen further back in time. And as we push toward the limits of observation, we approach what is sometimes called the edge of the observable universe. Not a physical boundary, but a horizon beyond which light has not yet had time to reach us since the beginning of the universe itself. Before James Webb, the deepest surveys conducted by Hubble and ground-based observatories had pushed this observational horizon back to redshifts around 11 or 12, corresponding to galaxies seen as they were roughly 400 million years after the Big Bang. Beyond that point, the light from any existing galaxies was stretched so far into the infrared that Hubble's instruments, optimized for shorter wavelengths, could barely detect it. The region of space and time beyond redshift 12 was known only through indirect inference, theoretical models of galaxy formation, computer simulations of cosmic structure, and observations of the cosmic microwave background radiation, the ancient afterglow of the Big Bang itself, which provides a snapshot of the universe as it was roughly 380,000 years after its beginning. Between that primordial snapshot and the first galaxies visible to Hubble lay a vast expanse of cosmic history often referred to as the Dark Ages, a period during which the first stars ignited, the first galaxies coalesced, and the first large-scale structures began to take shape, but during which almost no direct observational data existed. James Webb was designed to illuminate this era, to see the first light emerging from the darkness, and in doing so to fill in one of the most significant gaps in our understanding of cosmic history. What it found, however, was not merely the expected population of early, small, irregular galaxies struggling to form in the chaotic conditions of the infant universe. Instead, it revealed galaxies that appeared mature, structured, and organized into coherent patterns at redshifts and epochs where such organization was not supposed to exist in such abundance or clarity. These were not the tentative first flickerings of star formation, but fully realized galactic systems, some of them massive, some of them exhibiting signs of complex morphology, spiral arms, central bulges, features that current models suggested should take far longer to develop than the time available in the early universe. And more troubling still, these galaxies were not scattered randomly across the sky, but distributed in ways that suggested they were part of larger structures, filaments and walls extending across hundreds of millions of light years, an organized web of matter woven together by gravity and dark matter in an era when the universe was supposed to be far more homogeneous, far less differentiated than what the observations revealed. To understand the depth of the anomaly, one must consider how structure forms in the universe according to the prevailing cosmological model, the lambda-CDM framework that has successfully explained a wide range of observations over the past several decades. In this model, the universe began in a state of extreme uniformity, with matter and energy distributed almost perfectly evenly except for minuscule quantum fluctuations imprinted during the inflationary epoch, a brief period of exponential expansion in the first fraction of a second after the Big Bang. These tiny fluctuations, density variations of only 1 part in 100,000, were the seeds of all future structure. Regions that were slightly denser than average exerted slightly more gravitational pull, attracting surrounding matter and growing denser still over time. Meanwhile, regions that were slightly less dense than average lost matter to their neighbors and became increasingly empty, evolving into the voids we observe today. This process of gravitational amplification operated over billions of years, gradually transforming the nearly uniform early universe into the richly structured cosmos we see around us, with galaxies clustered into groups and superclusters, themselves arranged along vast filaments surrounding enormous voids, a cosmic web shaped by the invisible scaffolding of dark matter, a mysterious, non-luminous form of matter that interacts only through gravity and that comprises roughly 85% of the total mass in the universe. Dark matter, though invisible, dictates the architecture of cosmic structure. Its gravity pulls ordinary matter, protons, neutrons, electrons, the substance of stars and planets, into dense concentrations where galaxies can form. Computer simulations of cosmic evolution, which model the behavior of billions of dark matter particles over billions of years, reliably reproduce the large-scale filamentary structure of the universe observed today, lending strong support to the lambda-CDM model. But these simulations also make predictions about how long it should take for structure to form, how massive galaxies can be at different epochs, and how organized the cosmic web should appear at various look-back times. According to these predictions, the universe at redshifts beyond 6 or 7, corresponding to times less than 1 billion years after the Big Bang, should be dominated by relatively small, irregular galaxies still in the process of merging and growing. Large, well-ordered structures should be rare. The cosmic web should be present in nascent form, but not yet fully realized, not yet as clearly defined as it would become billions of years later. The galaxies James Webb found behind the known universe do not conform to these expectations. They're too numerous, too massive, too organized for the epoch in which they exist. Some exhibit redshifts greater than 13, placing them less than 300 million years after the Big Bang, in an era when the universe was barely 2% of its current age. Yet they appear not as formless clumps of gas struggling to ignite their first stars, but as structured systems, some with masses comparable to the Milky Way, arranged in patterns that suggest they are part of a larger, interconnected web extending across cosmological distances. This is not a subtle discrepancy, a minor deviation from the model that can be explained away with a tweak to a parameter. This is a fundamental challenge to the timeline of cosmic evolution, a revelation that forces us to question whether our understanding of how galaxies form and how structure arises is incomplete, or whether there are aspects of the early universe, physical processes, initial conditions, properties of dark matter or dark energy that we have not yet accounted for in our models. One possibility, explored cautiously by theorists in the wake of the initial data releases, is that the early universe was more inhomogeneous than previously assumed, that the initial conditions set by inflation were not as uniform as the cosmic microwave background suggests, or that processes during the dark ages amplified structure more rapidly than standard models predict. Perhaps the first stars were more massive and formed more quickly than expected, flooding their surroundings with energy and heavy elements that accelerated subsequent star formation and galaxy growth. Perhaps the behavior of dark matter in the extreme conditions of the early universe differs subtly from its behavior in later epochs, clumping more efficiently or interacting in ways that current simulations do not capture. Or perhaps the very nature of cosmic expansion in the first billion years was different, influenced by properties of dark energy or modifications to general relativity that only manifest under the extreme densities and temperatures of the early universe. Another, more provocative interpretation is that the galaxies James Webb has discovered are not simply further examples of the same cosmic web we have already mapped, but represent a distinct, previously hidden layer of structure that occupies regions of space excluded from earlier surveys by observational bias. Before Webb, deep surveys were conducted in narrow fields, tiny patches of sky observed with extreme sensitivity to capture the faintest possible sources. The most famous of these, the Hubble Ultra Deep Field, covered an area of sky smaller than a pinprick held at arm's length and revealed thousands of galaxies stretching back to the edge of Hubble's observational capability. But this approach, while effective at probing extreme distances in limited directions, left vast swathes of the sky less thoroughly examined, surveyed only at shallower depths or in wavelengths less suited to detecting highly redshifted sources. James Webb, with its superior infrared sensitivity and its ability to conduct wider field surveys more efficiently, has begun filling in these gaps, and in doing so has uncovered galaxies that were always there, always part of the cosmic web, but simply invisible to previous instruments. In this interpretation, the hidden web is not a new structure, but an extension of the known structure, rendered visible for the first time by technological advancement. Yet even this interpretation, which preserves the fundamental correctness of existing models, does not fully account for the density and organization of the newfound galaxies. If they were merely the faint tail of the luminosity distribution, the dimmest members of the known galaxy population, their numbers should decline smoothly with increasing distance and redshift, asymptotically approaching some limiting density. Instead, the data suggests clustering, filamentary arrangements, patterns that imply these galaxies are part of a coherent network extending beyond the boundaries of previous surveys. This coherence, this structural continuity, is what makes the discovery so significant and so unsettling. It is one thing to find more galaxies than expected. It is another to find them arranged in ways that suggest a vast, hidden architecture, a continuation of the cosmic web into realms we had assumed to be empty or at least too distant to survey in detail. To describe the structure as hidden is not to suggest it was deliberately concealed or that there is anything mysterious in the colloquial sense about its invisibility. It was hidden only in the sense that the light from these galaxies, stretched by billions of years of cosmic expansion into the deep infrared, was beyond the reach of instruments designed to observe in other wavelengths. The universe does not hide. We simply look with tools that reveal only a portion of what is there. Visible light telescopes see galaxies that emit or reflect visible light. Infrared telescopes see galaxies that emit in the infrared, whether due to star formation, dust emission, or cosmological redshift. Radio telescopes see synchrotron radiation from relativistic particles and the glow of cold hydrogen gas. X-ray observatories detect the hot plasma of galaxy clusters and the accretion disks of black holes. Each wavelength opens a different window onto the cosmos. And until we look through a particular window, the phenomena it reveals remain effectively invisible, part of the universe, but not part of our observable universe. James Webb opened a window into the deep infrared, and through that window, a hidden web emerged. This web, as it has come to be called in the literature, though the term is more poetic than precise, more evocative than rigorously defined, is not a single structure but a network of structures, a collection of filaments, walls, clusters, and voids extending across billions of light years and billions of years of cosmic time. It is hidden not because it exists in some parallel dimension or occupies a separate region of space, but because its galaxies, due to their extreme distance and the corresponding redshift of their light, were invisible to previous generations of telescopes. The known universe, as we understood it before James Webb, was not a false picture, but an incomplete one, a sketch drawn with the tools available at the time. What Webb has revealed is not a replacement for that sketch, but an extension, a continuation of the lines and patterns into regions the sketch did not cover. And in doing so, it has forced us to reconsider the scale and complexity of the cosmic web itself. The cosmic web is the largest scale structure in the universe, a three-dimensional lattice of galaxies and dark matter stretching from one horizon of the observable universe to the other. It was first recognized in the late 20th century as redshift surveys, projects that measured the distances to thousands of galaxies across large areas of sky, began revealing that galaxies are not distributed randomly, but are concentrated along filaments and walls, with vast, nearly empty voids in between. The pattern resembles a foam or sponge, with matter concentrated on the surfaces and edges of bubbles and very little in the interiors. This structure arises naturally from the gravitational amplification of primordial density fluctuations, the same process that drives the formation of individual galaxies and clusters, but operating on scales of hundreds of millions of light years rather than millions. Dark matter, which dominates the mass budget of the universe and governs the gravitational potential, collapses first into a filamentary network, and ordinary matter, gas, flows along these filaments, collecting in the densest regions where it cools, condenses, and eventually forms stars and galaxies. The cosmic web is thus both a map of where galaxies are and a map of the underlying dark matter distribution, a visible trace of an invisible architecture. Simulations of cosmic structure formation, run on supercomputers using the laws of gravity and the known properties of dark matter and dark energy, reproduce this web with striking fidelity. Feed the simulations the initial conditions implied by observations of the cosmic microwave background. Let the clock run forward for 13.8 billion years, and out comes a universe filled with filaments, walls, and voids, statistically indistinguishable from what we observe in large-scale surveys. This agreement between simulation and observation is one of the great successes of modern cosmology, a confirmation that we understand, at least in broad strokes, how structure forms and evolves. But simulations are only as accurate as the physics and assumptions built into them. And if the observations change, if new data reveals structure that the simulations did not predict, then the assumptions must be revisited. The hidden web discovered by James Webb challenges these assumptions not by contradicting the existence of the cosmic web, but by extending it in ways that were not anticipated. The simulations predicted a cosmic web, and observations confirmed it, but the observations were limited by the depth and wavelength coverage of the instruments available. Now, with deeper observations in the infrared, the web is seen to extend further, to include more galaxies, to possess more structure at early times than the simulation suggested. This may mean that the simulations are incomplete, that they do not fully capture the physics of the early universe, or it may mean that the initial conditions fed into them. The density fluctuations, the composition of matter and energy, were not quite right, that there are subtleties in the cosmic microwave background data or the inflationary models that we have not yet grasped. Or it may mean something more radical, that our understanding of how gravity operates on cosmological scales, or how dark matter behaves in the extreme conditions of the first billion years, requires revision. Some researchers have proposed that the hidden web is a relic of the epoch of reionization, the period roughly 200 million to 1 billion years after the Big Bang, during which the first stars and galaxies emitted enough ultraviolet radiation to ionize the hydrogen gas that filled the early universe. Before reionization, the universe was opaque to ultraviolet light, a fog of neutral hydrogen through which only infrared and longer wavelengths could pass. After reionization, that fog cleared and the universe became transparent, allowing light from distant galaxies to travel unimpeded to our telescopes. The process of reionization did not occur uniformly or instantaneously, but proceeded in a patchy, uneven manner, with regions around the first galaxies clearing first and the ionized zones gradually expanding and merging until the entire universe was ionized. The structure of these ionized zones would have been influenced by the distribution of early galaxies, which in turn was shaped by the underlying dark matter web. If the hidden web corresponds to regions of space that cleared early, becoming transparent sooner than average, then light from galaxies in those regions would have been able to escape and eventually reach us, while light from galaxies in regions that cleared later might have been absorbed or scattered, making those galaxies harder to detect. In this picture, the hidden web is not a separate structure, but a manifestation of the same cosmic web, revealed in a specific way by the physics of reionization. Others have speculated that the hidden web might be associated with primordial overdensities, regions of space that were slightly denser than average from the very beginning and that therefore collapsed into galaxies and clusters earlier than the average. If such overdensities were more common or more extreme than current models predict, they could account for the surprising abundance and organization of high redshift galaxies seen by James Webb. This would require revisiting the inflationary models that generate the initial density fluctuations, perhaps allowing for larger fluctuations on small scales or for features in the inflationary potential that create preferred scales of structure formation. Such modifications are not trivial. They would have consequences for many other aspects of cosmology and would need to be tested against a wide range of observations, from the cosmic microwave background to the distribution of galaxies at lower redshifts. But they represent the kind of theoretical flexibility that is often necessary when confronted with genuinely unexpected data. Still others have suggested that the hidden web might be evidence of a cosmological effect that we have not yet identified, something in the physics of cosmic expansion or the behavior of dark energy in the early universe that influences structure formation in ways not captured by standard models. Dark energy, the mysterious component that drives the accelerated expansion of the universe, is usually treated as a cosmological constant, a uniform energy density that remains constant over time. But there is no fundamental reason it must be constant. It could vary with time or space, and such variations could affect the rate and nature of structure formation. If dark energy was weaker or absent in the early universe, for example, gravity would have been more effective at pulling matter together, potentially speeding up the formation of galaxies and large-scale structure. Or if dark energy exhibited repulsive effects on certain scales, it might have influenced the distribution of matter in subtle ways that enhance the formation of filamentary structures. These ideas are speculative, lacking direct evidence, but they illustrate the range of possibilities that the hidden web has opened up for theoretical exploration. Regardless of the ultimate explanation, the mere existence of the hidden web has profound implications for how we map and understand the universe. For decades, cosmologists have spoken of the observable universe as if it were a well-defined, fully surveyed domain, a sphere roughly 93 billion light-years in diameter, centered on Earth, within which all matter and light that could have reached us since the Big Bang is in principle detectable. But detectability is not the same as detection. And the observable universe as cataloged in surveys and databases is far smaller than the observable universe in principle. There are vast regions of sky that have never been deeply surveyed, wavelengths that have never been systematically explored, faint galaxies that have never been individually cataloged. The known universe is a subset of the observable universe, and the boundaries of the known universe are set not by physics, but by technology and effort, by the sensitivity of our instruments and the time we have spent pointing them in various directions. James Webb is, in essence, expanding the known universe, pushing its boundaries outward and backward in time, filling in the gaps left by earlier surveys. But it is doing so in a way that reveals not just more of the same, but new patterns, new structures, new aspects of cosmic architecture that were invisible before. The hidden web is a reminder that the universe is larger, more complex, and more intricately structured than our maps have shown, and that each new generation of instruments does not merely refine the picture, but fundamentally changes it, revealing layers of reality that previous generations could only infer or imagine. Consider the scale of what has been revealed. The galaxies that make up the hidden web are distributed across billions of light years, extending from regions just beyond the boundaries of previous surveys out to distances corresponding to the first few 100 million years after the Big Bang. The filaments and walls they trace are comparable in scale to the largest known structures in the universe: superclusters, great walls, the Sloan Great Wall, the Hercules Corona Borealis Great Wall, but exist at epochs when such structures were not supposed to be fully formed. The volume of space that these galaxies occupy is immense, a significant fraction of the observable universe, and the number of galaxies involved likely runs into the hundreds of thousands or millions, though complete counts will require years of additional observation and analysis. Each of these galaxies is itself a complex system containing billions or tens of billions of stars, surrounded by halos of dark matter, hosting gas, dust, possibly planets, and perhaps even life, though the conditions in the early universe make the latter seem unlikely. Each one has a history, a story of formation and evolution, and together they form a collective history, a narrative of how structure arose in the cosmos during an epoch that until now has been only dimly understood. The process of mapping this hidden web is ongoing and will likely continue for decades. James Webb, despite its remarkable capabilities, observes only small patches of sky at a time, and even with its efficient infrared instruments, it takes hours or days of exposure to reach the depths necessary to detect the faintest galaxies at the highest redshifts. Systematic surveys are being conducted, targeting specific regions known to be rich in high redshift sources or chosen to provide representative samples of the universe at different epochs. Spectroscopy, the measurement of the precise wavelengths of light from individual galaxies, is used to determine redshifts accurately, allowing astronomers to construct three-dimensional maps showing not just the positions of galaxies on the sky, but their distances and thus their arrangement in space. These maps, as they accumulate, will reveal the detailed structure of the hidden web, its filaments and nodes, its density contrasts and voids, and will allow comparisons with simulations to test whether existing models can be adjusted to match the observations or whether more fundamental changes are required. Already, early results from Webb have prompted revisions to models of galaxy formation. Simulations are being rerun with adjusted parameters, higher star formation efficiencies, earlier onset of metal enrichment, more efficient cooling mechanisms, to see if these changes can reproduce the abundance and properties of high redshift galaxies without violating constraints from other observations. Some simulations have incorporated more detailed physics, including feedback from supermassive black holes, which can inject energy into their surroundings and influence the rate at which gas collapses into stars. Others have experimented with different assumptions about the initial mass function of stars, the distribution of masses among stars formed in a given burst of star formation, since more massive stars produce more light and more heavy elements per unit mass, potentially allowing galaxies to become bright and chemically enriched more quickly than standard assumptions predict. These are incremental adjustments, Tweaks to the models aimed at preserving the overall framework of lambda-CDM cosmology while accommodating the new data. Whether they will prove sufficient remains to be seen. But there is also the possibility, acknowledged by many researchers though rarely discussed in detail in the published literature, that the hidden web is telling us something more fundamental, that it is evidence not just of incomplete models, but of gaps in our understanding of the universe itself. Dark matter, for instance, is inferred from its gravitational effects. The rotation curves of galaxies, the dynamics of galaxy clusters, the patterns of gravitational lensing, the structure of the cosmic microwave background, but has never been directly detected. We do not know what particle or particles constitute it, how they interact beyond gravity, or whether their properties might change under different conditions. If dark matter behaves differently in the early universe than it does today, clumping more efficiently or interacting weakly with ordinary matter or radiation in ways that leave no trace in later epochs, that could affect the rate and pattern of structure formation in ways not captured by current simulations. Such modifications to dark matter physics are highly constrained by existing observations, but not impossible, and the hidden web might provide the impetus to explore them more seriously. Similarly, dark energy, the component that dominates the energy budget of the universe today and drives its accelerated expansion, is even more mysterious than dark matter. It is usually treated as a cosmological constant, but there is no deep theoretical understanding of why it exists, what its value is, or whether it truly is constant. If dark energy evolves over time, increasing or decreasing in strength as the universe ages, that would affect the expansion rate at different epochs, which in turn would affect the growth of structure. A weaker dark energy in the early universe would mean slower expansion, giving gravity more time to pull matter together and form galaxies and clusters. The hidden web, with its unexpectedly mature and organized galaxies at early times, might be a hint that dark energy was indeed weaker in the past, though disentangling this effect from other factors, such as the efficiency of star formation or the initial density of fluctuations, will require careful analysis of a wide range of data. There is also the question of whether the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, holds as strictly as we have assumed. This principle, which underlies all of modern cosmology, asserts that on average, every location in the universe is equivalent to every other location, and every direction is equivalent to every other direction. It is an assumption of symmetry, simplifying the mathematics of general relativity and allowing us to construct models of the universe as a whole. Observations of the cosmic microwave background, which is remarkably uniform across the sky with temperature variations of only 1 part in 100,000, provide strong support for the cosmological principle. But the cosmic microwave background shows the universe as it was 380,000 years after the Big Bang, and it is possible that on smaller scales or at different epochs, the universe is less homogeneous than the principle suggests. The hidden web, with its dense concentrations of galaxies in some directions and apparent voids in others, raises the question of whether large-scale structure is distributed as evenly as the cosmological principle requires, or whether there are significant variations that our models have not accounted for. Some studies have reported evidence of anomalously large structures in the universe, walls and filaments extending across scales that approach or exceed the homogeneity scale, the scale above which the universe should appear smooth and featureless according to the cosmological principle. These reports are controversial, often questioned on methodological grounds or attributed to observational biases, but they persist in the literature, and the hidden web adds to the accumulating evidence that the universe may be lumpier on large scales than the standard model comfortably accommodates. If this is true, it would not necessarily overturn cosmology entirely. The cosmological principle could still hold as a statistical average, even if individual regions deviate significantly, but it would require a more nuanced understanding of structure formation and a more careful consideration of how local inhomogeneities might affect measurements of cosmological parameters. The implications of the hidden web extend beyond theoretical cosmology into the realm of observational strategy, and the philosophy of science itself. Every model of the universe is built on a foundation of data, and data is gathered by instruments that observe specific wavelengths, specific regions of sky, specific types of sources. The choices we make about what to observe, where to point our telescopes, how long to expose, and which wavelengths to prioritize inevitably shape the picture we construct. For decades, the optical and near-infrared wavelengths accessible to Hubble and ground-based telescopes defined the boundaries of deep field surveys, and the galaxies detected in those wavelengths defined our understanding of the high-redshift universe. But those choices, reasonable and well-justified as they were, introduced a bias, a selection effect that excluded galaxies whose light had been redshifted beyond the range of those instruments. The hidden web existed all along, but it was invisible to our surveys, and so it did not appear in our catalogs, our simulations, or our models. Only by extending our observations into new wavelength regimes, by pushing the sensitivity and coverage of our instruments beyond previous limits, could the hidden web be revealed. This is a lesson that repeats throughout the history of astronomy. Every major advance in instrumentation has revealed phenomena that were invisible before, often challenging or overturning prevailing theories. The invention of the telescope allowed Galileo to see the moons of Jupiter and the phases of Venus, observations that contradicted the geocentric model and supported the heliocentric view. The development of photography and spectroscopy in the 19th century revealed the chemical composition of stars and the existence of galaxies beyond the Milky Way, transforming astronomy from a discipline concerned with positions and motions into one concerned with the nature and evolution of celestial objects. The construction of radio telescopes in the mid-20th century opened a new window onto the universe, revealing quasars, pulsars, and the cosmic microwave background, phenomena that had no counterpart in optical astronomy and that forced the development of entirely new theoretical frameworks. Infrared astronomy, which came of age in the late 20th century with missions like IRAS and Spitzer, revealed dust-obscured star formation and cool objects like brown dwarfs and debris disks, again expanding the catalog of known phenomena. And now, with James Webb, the deepest and most sensitive infrared observatory ever built, the hidden web has emerged, a structure that was always part of the universe, but never part of our observed universe until the technology existed to detect it. This pattern of technological advancement revealing hidden aspects of reality raises a philosophical question that is both humbling and unsettling. How much of the universe remains hidden, not because it is fundamentally unobservable, but simply because we have not yet built the instruments to observe it? The hidden web was hidden only because we lacked infrared telescopes with sufficient sensitivity. What other structures, phenomena, or aspects of cosmic architecture are invisible to us now, waiting to be revealed by the next generation of instruments or the generation after that? The observable universe, as we define it, is limited by the speed of light and the age of the universe. Light from beyond a certain distance has not yet had time to reach us, but the detectable universe, the portion we have actually observed and cataloged, is far smaller, limited by the capabilities of our technology and the finite amount of time we have spent observing. Every advance pushes the boundary of the detectable universe closer to the boundary of the observable universe, but the gap between them remains vast, and within that gap lie unknown structures, perhaps entire populations of objects that we can infer must exist, but that we have never seen. The hidden web, then, is not merely a specific discovery about a specific set of galaxies, though it is certainly that. It is also a reminder of the incompleteness of our knowledge, a demonstration that the universe is larger and more complex than our current maps suggest, and that those maps, detailed and accurate as they may be within their surveyed regions, remain partial sketches of a grander tapestry. This realization does not diminish the achievements of previous generations of astronomers, whose work laid the foundation for what we know today, but it does place those achievements in context as steps in a longer journey rather than as the final word. The known universe is always a provisional concept, always subject to expansion and revision as new data arrives. and the hidden web is the latest illustration of this fundamental truth. To understand how the hidden web fits into the broader picture of cosmic structure, it is necessary to consider the hierarchical nature of structure formation, the process by which small-scale inhomogeneities grow into ever larger structures over time. In the early universe, immediately after the Big Bang, matter was distributed almost uniformly, with only tiny quantum fluctuations imprinted by inflation to distinguish one region from another. These fluctuations, though minuscule, were amplified by gravity over billions of years, growing into the structures we see today. The process begins at the smallest scales, with the first density enhancements collapsing to form dark matter halos, regions where dark matter has clumped together under its own gravity. Gas, which follows the gravitational potential set by dark matter, flows into these halos, cools, and eventually forms stars, creating the first galaxies. These first galaxies are small, irregular, and faint, the building blocks of larger galaxies that form later through mergers and accretion. As time passes, gravity continues to pull matter together on ever larger scales. Small galaxies merge to form larger galaxies. Groups of galaxies fall together to form clusters, and clusters themselves are organized along filaments, the threads of the cosmic web. This hierarchical process is bottom-up, meaning the small structures form first and then assemble into larger structures over time. It is a direct consequence of the properties of dark matter and gravity, and it is robustly predicted by simulations and well supported by observations of the local universe, where we can trace the history of individual galaxies and clusters through detailed studies of their stars, gas, and structure. But the hidden web challenges the simple bottom-up picture, at least in its timing. If the galaxies James Webb has found at high redshifts are already massive and already organized into filamentary structures, it suggests that the hierarchical assembly process proceeded more rapidly in the early universe than standard models predict, or that it was seeded by initial conditions that favored the formation of large structures at early times. This does not necessarily mean the bottom-up framework is wrong, but it does mean that the details, how quickly small halos merge, how efficiently gas cools and forms stars, how the first galaxies influence their surroundings through feedback, may need to be revised to match the observations. One factor that could accelerate structure formation is the efficiency of gas cooling. In the early universe, the gas that fills dark matter halos is hot, heated by the gravitational energy released as it falls into the halo. For stars to form, this gas must cool and condense into dense clouds, and the rate at which it cools depends on the presence of elements heavier than hydrogen and helium, what astronomers call metals, even though in this context the term includes elements like carbon, oxygen, and nitrogen. These metals are produced by stars and dispersed into the surrounding gas when stars explode as supernovae or shed their outer layers at the end of their lives. In the very first generation of stars, which formed from pristine gas containing no metals, cooling was slow and inefficient, limiting the rate of star formation. But as soon as the first stars exploded and enriched the gas with metals, subsequent generations of stars could form more quickly and more efficiently. If the first stars were very massive and very short-lived, exploding after only a few million years and distributing their metals widely, they could have accelerated the pace of galaxy formation across the early universe, allowing the massive, well-organized galaxies seen by James Webb to form earlier than expected. Another factor is feedback, the process by which energy released by stars and supermassive black holes affects the surrounding gas, either by heating it and preventing it from cooling or by expelling it from the galaxy entirely, shutting down star formation. Feedback is a critical component of modern galaxy formation models, invoked to explain why galaxies are not more massive than they are, why star formation rates are not higher, and why the relationship between galaxy mass and dark matter halo mass follows the observed pattern. But feedback is poorly understood in detail, difficult to simulate accurately, and may operate differently in the early universe than it does today. If feedback was weaker in the first billion years, either because the first supermassive black holes had not yet grown large enough to inject significant energy, or because the gas density was higher and harder to expel, then galaxies could have formed stars more efficiently and become more massive more quickly, potentially explaining the properties of the hidden Webb's galaxies. Yet, even with these adjustments, more efficient cooling, weaker feedback, more massive first stars, it remains challenging to explain the degree of organization seen in the hidden Webb. The fact that these early galaxies are not scattered randomly, but arranged in filaments and walls, structures that in the local universe are associated with the mature cosmic web. This organization suggests that the underlying dark matter distribution was already highly structured at early times, more structured than simulations starting from the standard initial conditions predict. One way to achieve this is to increase the amplitude of the initial density fluctuations on certain scales, allowing structure to collapse earlier and more completely. But this is constrained by observations of the cosmic microwave background, which measures the amplitude of fluctuations at the time the universe became transparent, and by observations of the local universe, which must also be consistent with the same initial conditions. Adjusting the initial conditions to fit the high redshift observations without violating low redshift constraints is a delicate balancing act, and it is not yet clear whether it can be done within the standard inflationary framework. An alternative is to consider modifications to the physics of structure formation itself, changes to the way dark matter behaves, or the way gravity operates on cosmological scales. Some researchers have proposed that dark matter might interact with ordinary matter or with itself through forces other than gravity, interactions that would affect how it clumps and how quickly structure forms. These interactions must be weak, since strong interactions would leave detectable signatures in many other observations. But even weak interactions could potentially speed up or enhance structure formation under certain conditions. Other researchers have explored modifications to gravity, theories in which the force of gravity is slightly different on large scales or at early times than it is locally and today. These modified gravity theories are often motivated by attempts to explain dark energy without invoking a new form of energy, but some versions also affect the growth of structure, and in principle, they could be tuned to produce more rapid structure formation in the early universe. Both self-interacting dark matter and modified gravity are highly speculative, lacking direct evidence, and they face significant challenges in matching the full range of cosmological observations. But they represent the kind of out-of-the-box thinking that unexpected discoveries like the hidden web can inspire. There's also the question of what the hidden web tells us about the cosmic web as a whole, about the extent and coherence of large-scale structure across the observable universe. If the web seen by James Webb is a continuation of the same web we observe locally, then it implies that the cosmic web is not just a feature of the late-time universe, but has been in place, in some form, since very early times, evolving and growing denser over the eons, but maintaining a consistent architecture from the first billion years to the present. This continuity would be a powerful confirmation of the hierarchical structure formation paradigm, showing that the same physical processes, gravity, dark matter, gas dynamics, operate across cosmic time and produce a single, unified web that spans the entire observable universe. On the other hand, if the hidden web is somehow distinct, if it exhibits properties or patterns that do not connect smoothly to the known web, that would be deeply puzzling and might suggest that different regions of the universe at different epochs follow different evolutionary paths, perhaps due to variations in initial conditions or environmental factors that we have not yet identified. Current data does not yet allow a definitive answer to this question. The observations from James Webb are still being analyzed. The redshifts of many galaxies are still being measured, and the three-dimensional structure of the hidden web is still being pieced together from observations taken over multiple observing campaigns. It will likely take years, possibly decades, to fully map the hidden web and understand its relationship to the rest of the cosmic web. But the very fact that this structure exists, that it is coherent and organized and contains vast numbers of galaxies, is already a major discovery, one that will shape the direction of extragalactic astronomy and cosmology for the foreseeable future. One of the more profound implications of the hidden web is its effect on our understanding of the cosmic census, the effort to count and catalog all the galaxies in the universe. Estimates of the total number of galaxies have varied over the years, depending on the depth and coverage of surveys and the assumptions made about galaxy populations that are too faint or too distant to observe directly. Before James Webb, the most commonly cited estimate was that there are roughly 200 billion galaxies in the observable universe, a number derived from deep Hubble surveys and extrapolated to cover the entire sky and the full range of distances. But this estimate, like all such estimates, depended on assumptions about the luminosity function of galaxies, the distribution of galaxy brightnesses, and about how that function evolves with redshift. If high redshift galaxies are more numerous or more luminous than those assumptions allowed, then the total count could be significantly higher. The hidden web suggests that the count is indeed higher, potentially much higher. Every additional galaxy discovered in the deep infrared surveys conducted by James Webb adds to the census. And if these galaxies represent a population that was systematically underestimated in previous surveys, then the total number could be revised upward, perhaps to 300 billion, 400 billion, or more. The exact number depends on the completeness of the Webb surveys, the corrections for observational biases, and a modeling of galaxy populations at redshifts beyond what could be directly observed. But the direction of the revision is clear. The universe contains more galaxies than we previously thought, and those galaxies extend to greater distances and earlier epochs than the known universe, as cataloged before Webb encompassed. This upward revision has implications not only for our understanding of galaxy formation and cosmic structure, but also for the total amount of light in the universe, a quantity known as the extragalactic background light. This background is the sum of all the light emitted by all the stars and all the galaxies throughout cosmic history, redshifted and spread across the sky. It is difficult to measure directly because it is faint and contaminated by foreground sources like the zodiacal light, sunlight reflected off dust in the solar system, and the emission from stars in our own galaxy. But estimates based on galaxy counts and models of stellar populations suggest a certain level of background light, and if the galaxy count increases due to the discovery of the hidden web, the background light should increase correspondingly. Future measurements of the extragalactic background light, particularly in the infrared, where the contribution from high redshift galaxies is concentrated, could provide an independent check on the census and on the completeness of our surveys. The hidden web also has implications for the study of galaxy evolution, the process by which galaxies change over time, growing in mass, altering their star formation rates, developing distinct morphologies, and assembling the stellar populations we observe today. Galaxy evolution is studied through a combination of observations at different redshifts, which provides snapshots of galaxies at different stages of their lives, and through simulations that model the processes driving those changes. By comparing the properties of galaxies at high redshifts, such as their masses, sizes, star formation rates, and chemical compositions, to the properties of galaxies at low redshifts, astronomers can trace how galaxies evolve and test models of the physical processes involved. The galaxies in the hidden web, observed at redshifts greater than 10, 11, or even 13, provide some of the earliest snapshots available, showing what galaxies looked like only a few 100 million years after the Big Bang. These early galaxies, as revealed by James Webb, are in many cases more massive, more luminous, and more chemically enriched than models predicted, suggesting that star formation began earlier, proceeded more rapidly, or was more efficient than previously thought. They also exhibit a wider range of morphologies than expected, from irregular, clumpy systems to galaxies with surprising signs of order, such as rotating disks or central bulges. These properties constrain the processes that shaped the first galaxies: how gas was accreted, how stars formed, how supernovae and supermassive black holes provided feedback, and how mergers assembled larger systems from smaller ones. By studying the hidden web, astronomers are learning about the conditions in the early universe and how those conditions influence the trajectory of galaxy evolution. One particularly intriguing aspect of the hidden web is the potential presence of extremely massive galaxies at very high redshifts, systems with stellar masses comparable to the Milky Way or even larger, existing less than 1 billion years after the Big Bang. Such galaxies are difficult to explain within the standard hierarchical formation framework, which predicts that massive galaxies assemble gradually over time through the mergers of smaller systems. If a galaxy with 100 billion solar masses of stars is observed at redshift 12, corresponding to an age of the universe of only 400 million years, it means that somehow 100 billion solar masses worth of gas was converted into stars in less than 400 million years, a rate of star formation that seems almost implausibly high. Even if star formation began immediately after the Big Bang, which it could not have, since the first stars likely took tens of millions of years to form, the average star formation rate required to build such a galaxy is hundreds or even thousands of solar masses per year, far exceeding the rates observed in the most vigorous star-forming galaxies in the later universe. There are several possible explanations for such massive early galaxies, none of them entirely satisfactory. One is that the stellar mass estimates are wrong, inflated by some systematic error in the method used to infer mass from observed light. Stellar masses are not measured directly, but are inferred from the brightness of a galaxy and assumptions about the types of stars it contains, the star formation history, and the amount of dust obscuring the light. If the assumptions are incorrect, for example, if the early galaxies contain more massive stars than typical, or if dust extinction is higher than assumed, then the inferred masses could be overestimated. But the discrepancies seem too large to be explained entirely by such errors, and multiple independent methods for estimating mass yield similar results, suggesting that the masses are real. Another explanation is that star formation in the early universe was sustained at high rates for longer periods than current models allow. Perhaps the supply of gas was larger, or the efficiency of converting gas into stars was higher, or feedback processes that would normally shut down star formation were delayed or weakened. If the first galaxies experienced a prolonged starburst, an episode of rapid star formation lasting tens or hundreds of millions of years without interruption, they could accumulate large stellar masses quickly. But this requires fine-tuning several aspects of the star formation process, and it is not clear why such conditions would be common in the early universe. A third possibility is that these massive early galaxies are not individual systems, but are the result of mergers, multiple smaller galaxies colliding and coalescing into a single larger galaxy. Mergers are a common part of galaxy evolution, particularly in the early universe when galaxies were closer together and collisions more frequent. If the observed massive galaxies are recent merger products, their stellar masses would represent the sum of their progenitors, potentially making the total mass less surprising. But even this explanation has limits, since the progenitors themselves must have formed quickly, and the mergers must have occurred very early, which pushes the problem back in time, but does not entirely solve it. Regardless of the explanation, the existence of such massive galaxies at high redshifts, if confirmed by ongoing observations and analysis, represents a significant challenge to the standard model of galaxy formation and may require new physics or new mechanisms to be incorporated into the models. The hidden web, by revealing these galaxies and many others like them, is forcing a re-examination of how galaxies form and evolve, a process that is still unfolding as more data becomes available. Another important aspect of the hidden web is what it reveals about the distribution of dark matter in the early universe. Dark matter, though invisible, dictates where and when galaxies form, since its gravity provides the potential wells into which ordinary matter falls. The arrangement of galaxies in the hidden web, their clustering, the filaments they trace, the voids between them, reflects the underlying distribution of dark matter, and by mapping the galaxies, astronomers can infer the structure of the dark matter web. This is done through a combination of direct observations, such as the clustering statistics of galaxy positions and gravitational lensing, the bending of light by dark matter concentrations, which distorts the shapes of background galaxies and allows the mass distribution to be reconstructed. Early results from James Webb suggest that dark matter in the early universe is clumped into filaments and halos in much the same way as it is today, but with some differences in the details. The halos that host the first galaxies appear to be less massive on average than the halos that host later galaxies, consistent with the bottom-up formation picture, but there are hints that the filaments connecting these halos may be denser or more coherent than simulations predict, possibly indicating that dark matter collapsed more efficiently at early times. These hints are tentative, based on limited data and preliminary analyses, but they point toward a more nuanced understanding of dark matter dynamics, one that may require adjustments to the standard model or the inclusion of additional physics. There is also the question of whether the hidden web contains evidence of dark matter substructure, small-scale clumps or halos within the larger filaments and clusters that have not yet merged into bigger systems. Substructure is a natural consequence of hierarchical formation, as smaller halos merge to form larger ones. Some infalling halos survive as distinct entities orbiting within the larger halo, creating a population of subhalos. Detecting substructure in the early universe is challenging, since the subhalos are small and contain few stars, making them difficult to observe directly. But their presence can be inferred from the clustering properties of galaxies or from gravitational lensing. In future studies of the hidden web may reveal how common substructure is and how it evolves over time. The discovery of the hidden web also has implications for the study of the intergalactic medium, the diffuse gas that fills the space between galaxies. This gas, which comprises the majority of the ordinary matter in the universe, is extremely tenuous and difficult to observe directly, except when it is ionized and emits or absorbs light at specific wavelengths. One of the most powerful tools for studying the intergalactic medium is the observation of quasars, extremely bright objects powered by supermassive black holes, whose light passes through the intergalactic medium on its way to us, getting absorbed by intervening gas clouds. By analyzing the absorption lines in quasar spectra, astronomers can map the distribution of gas along the line of sight and infer its density, temperature, and ionization state. The hidden web, with its dense concentrations of galaxies at high redshifts, likely had a significant effect on the intergalactic medium during the epoch of reionization. The ultraviolet radiation emitted by stars in these galaxies would have ionized the surrounding gas, creating bubbles of ionized hydrogen that expanded and eventually merged, transforming the universe from a neutral, opaque state to an ionized, transparent one. The structure of these ionized bubbles would have been influenced by the distribution of galaxies, which in turn was shaped by the underlying dark matter web, meaning that the hidden web played a role in determining the pattern and timing of reionization. Observations of the intergalactic medium at high redshifts, combined with observations of the galaxies in the hidden web, can provide insights into how reionization proceeded and how it was affected by the large-scale structure of the universe. Beyond its implications for cosmology and galaxy formation, the hidden web raises questions about the nature of observation and the limits of knowledge. Every observation of the universe is made from a particular location, in our case, Earth, and at a particular time, and it is limited by the finite speed of light, the finite sensitivity of our instruments, and the finite amount of time we have spent observing. The observable universe is, in principle, a sphere centered on us, containing all the matter and light that could have reached us since the Big Bang. But this sphere is not fixed. It grows over time as light from more distant regions reaches us, and it will continue to grow for billions of years until the accelerated expansion driven by dark energy carries distant galaxies beyond the horizon, redshifting their light so severely that it becomes undetectable. The hidden web, though invisible to previous telescopes, was always within the observable universe, always part of the sphere of space from which light could reach us. It was hidden not by any physical barrier, but by the limitations of our technology, and its revelation is a demonstration that the boundary between the observable and the unobservable is not fixed, but is constantly being pushed outward by the development of more powerful instruments. This realization prompts a deeper question. What lies beyond even the hidden web, in the regions of space so distant that their light has not yet reached us, or in directions we have not yet surveyed, or at wavelengths we have not yet explored? The universe does not end at the edge of our observations. It extends, perhaps infinitely, beyond the horizon, containing structures and phenomena that we can infer must exist, but that we cannot yet see. Every new instrument, every new survey, every new wavelength band opens a window onto a previously hidden part of this vast expanse, revealing layers of complexity that were invisible before. The hidden web is one such layer, but it will not be the last. Future telescopes, observing in wavelengths inaccessible to James Webb, or with sensitivities far exceeding its own, will doubtless reveal further layers, further structures, further aspects of the universe that are hidden from us now, but that will become known as technology advances. There is a certain humility in this recognition, an acknowledgement that our knowledge, however extensive it may seem, is always incomplete, always provisional, always subject to expansion and revision. The known universe is a construct, a map drawn from the data we have gathered, and like all maps, it is a simplified representation of a far more complex reality. It shows the features we have observed in the detail our instruments allow, but it omits everything we have not yet seen, and it is bounded by the limits of our technology rather than by any natural boundary. The hidden web is a reminder that the universe is larger than our maps, richer in structure and detail, and that every advance in observational capability reveals not just more of the same, but new and unexpected phenomena that challenge our understanding and force us to think more deeply about the nature of the cosmos. The process of discovery in astronomy is cumulative and iterative. Each generation builds on the work of the previous, using better instruments to see further and more clearly, and each new observation refines or revises the models and theories constructed from earlier data. The hidden web is a product of this process, a discovery made possible by the development of infrared technology over decades, the construction of space-based observatories free from the blurring and absorption of Earth's atmosphere, and the patient accumulation of observing time on targets carefully chosen to probe the limits of the observable universe. It is the result of thousands of hours of observation, years of data analysis, and the collaboration of scientists across continents and disciplines, all working toward the common goal of understanding the cosmos. But it is also a discovery that, in revealing new structures and new questions, opens up new avenues of research that will occupy astronomers for decades to come. The mapping of the hidden web has only just begun. Many of the galaxies discovered in the early images from James Webb have not yet been studied in detail. Their redshifts, their masses, their star formation rates, their chemical compositions, their dynamics. All of these properties must be measured through follow-up observations, spectroscopy, and detail modeling. The three-dimensional structure of the web, the connections between filaments, the locations of dense nodes and empty voids, must be reconstructed from observations taken at different times and in different directions, a painstaking process that will require extensive use of James Webb and other telescopes over many years. Moreover, the hidden web is not a static structure. The galaxies within it are evolving, forming stars, merging with neighbors, interacting with the intergalactic medium, and responding to the feedback from supernovae and black holes. By observing these galaxies at different stages of their lives, by comparing galaxies at redshift 13 with galaxies at redshift 10, 8, 6, and so on, astronomers can trace the evolutionary pathways that lead from the first small, irregular systems to the massive, well-ordered galaxies we see in the local universe. The hidden web provides snapshots from the earliest stages of this process, a window onto an epoch that until now has been largely inaccessible. And these snapshots will be integrated with observations at lower redshifts to construct a complete picture of galaxy evolution across cosmic time. There is also the question of how representative the hidden web is of the universe as a whole. The observations from James Webb, though deeper and more sensitive than any before them, still cover only a small fraction of the sky. If the galaxies discovered so far are typical, then extrapolating their density and distribution across the entire sky yields the revised census and the extended map of the cosmic web. But if they are atypical, if the regions surveyed by Webb happen to be unusually dense or unusually structured. Then the extrapolation could be misleading, and the true extent of the hidden web might be different from current estimates. Determining whether the observed regions are typical requires surveying additional areas of sky, comparing the properties of galaxies in different directions, and looking for large-scale variations in density or structure that might indicate inhomogeneities in the universe. Such variations, if they exist, would be important not only for understanding the hidden web, but also for cosmology more broadly. The cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales, is fundamental to the standard model of cosmology, and any evidence that the universe is significantly inhomogeneous on scales larger than a few 100 million light-years would challenge that principle and require a rethinking of how we model the universe. The hidden web, by extending the map of large-scale structure into previously unsurveyed regions, provides new data that can be used to test the cosmological principle and to search for deviations from homogeneity. So far, the structure revealed by Webb appears consistent with an extension of the cosmic web as we know it, but the data is still incomplete, and it is too early to draw definitive conclusions. Another area where the hidden web has implications is in the study of the universe's missing baryons, a long-standing puzzle in cosmology. Baryons are the ordinary matter particles, protons and neutrons, that make up atoms, stars, planets, and gas, and the total amount of baryonic matter in the universe is well constrained by observations of the cosmic microwave background and by measurements of the abundances of light elements produced in the first few minutes after the Big Bang. However, when astronomers count up all the baryons they can observe directly, in stars, in the cold gas of galaxies, in the hot gas of galaxy clusters, they find that only about half of the expected baryonic matter is accounted for. The rest, the missing baryons, are believed to reside in a diffuse, warm-hot intergalactic medium that is difficult to observe because it is too hot to emit efficiently in the optical or infrared and too diffuse to produce strong emission or absorption lines. The hidden web, with its dense filaments and concentrations of galaxies, is likely associated with regions of enhanced baryon density, where the intergalactic medium is compressed and heated by gravitational collapse and by the energy output of the galaxies themselves. Observations of this medium, using techniques such as X-ray emission from hot gas or the Sunyaev-Zel'dovich effect, a distortion of the cosmic microwave background caused by scattering off hot electrons, could reveal the presence of the missing baryons in the filaments of the cosmic web, including those traced by the hidden web. James Webb, though not designed primarily for X-ray or microwave observations, can contribute to this effort by identifying the locations and properties of the galaxies that trace the web, providing targets for follow-up observations with other telescopes. Over time, a combined view from multiple wavelengths and multiple instruments will build a complete picture of the hidden web, encompassing not only the galaxies themselves, but also the dark matter and baryonic matter that surrounds them and connects them. The discovery of the hidden web also has resonance beyond astronomy, touching on broader themes in science and human understanding. It is a reminder that reality is always more extensive than our perception of it, that the world we observe is shaped by the tools we use to observe it, and that every advance in those tools reveals aspects of reality that were previously invisible. This is true not only in astronomy, but in every field of science, from physics to biology to neuroscience. The microscope revealed cells and microorganisms, transforming our understanding of life. The particle accelerator revealed quarks and bosons, transforming our understanding of matter. The neuroimaging scanner revealed the activity of the living brain, transforming our understanding of mind. Each of these instruments opened a window onto a hidden layer of reality, a domain that existed all along, but that was inaccessible to direct observation until the technology was developed to detect it. The hidden web is astronomy's latest example of this phenomenon, a layer of cosmic structure that was always there, part of the universe, but hidden from view by the limitations of previous telescopes. Its discovery is a triumph of technology and human ingenuity, the result of decades of effort to design, build, and deploy an observatory capable of seeing, what had never been seen before. But it is also a testament to the open-ended nature of scientific inquiry, the fact that no matter how much we learn, there's always more to discover, always deeper questions to ask, always further horizons to explore. The universe does not yield its secrets easily, and every answer we obtain raises new questions, new puzzles, new mysteries that drive the next generation of research. In this sense, the hidden web is not an endpoint, but a beginning, the opening of a new chapter in our ongoing effort to understand the cosmos. The galaxies it contains, the structures they form, the processes that shape them, all of these are subjects of intense study now, and they will remain so for years, probably decades to come. The data from James Webb will be analyzed and reanalyzed, compared with simulations, used to test theories, and eventually integrated into a revised picture of cosmic history that incorporates the existence and properties of the hidden web. But even as this work proceeds, new questions will emerge, new observations will be planned, and new instruments will be developed to push the boundaries of the detectable universe still further. The cycle of discovery is continuous, each answer leading to new questions, each observation revealing new layers of complexity, and the hidden web is simply the most recent step in this unending journey. The structure and properties of the hidden web also invite comparisons with the known cosmic web, the large-scale structure that has been mapped in the local universe over the past several decades. The local cosmic web is characterized by a hierarchy of structures, from individual galaxies to groups and clusters, arranged along filaments that connect dense nodes with vast voids in between. The densest nodes, where multiple filaments intersect, are the sites of massive galaxy clusters, concentrations of hundreds or thousands of galaxies bound together by gravity, their motions governed by the immense mass of dark matter that pervades the cluster. The filaments themselves are rivers of galaxies, stretching across hundreds of millions of light years, tracing the paths along which matter flows under the influence of gravity. The voids, in contrast, are regions of extremely low density, where galaxies are rare and the expansion of space proceeds more rapidly than in denser regions, creating a kind of cosmic emptiness that accounts for much of the volume of the universe. This structure is not random, but is the predictable outcome of gravitational collapse acting on the initial density fluctuations present in the early universe. The simulations that reproduce the cosmic web start with a nearly uniform distribution of dark matter particles, perturbed by small, random fluctuations, and evolve the system forward in time according to the laws of gravity and the expansion of the universe. As the simulation progresses, the fluctuations grow, dense regions attract more matter and become denser, and the matter organizes itself into a web-like pattern, with filaments, nodes, and voids emerging naturally from the dynamics. The agreement between these simulations and the observed structure of a local universe is one of the great successes of modern cosmology, a confirmation that the basic physics of structure formation is well understood. But the hidden web, observed at much earlier times, tests whether that same physics applies in the early universe, when conditions were very different from today. The universe at redshift 10 or 12 is younger, denser, hotter, and more rapidly expanding than the universe today. The dark matter halos are smaller, the galaxies are younger, the intergalactic medium is still in the process of being ionized, and the influence of dark energy, which drives the accelerated expansion in the late universe, is negligible. Despite these differences, the hidden web exhibits the same basic structure as the local web: filaments, nodes, voids, suggesting that the process of gravitational collapse and structure formation operates in much the same way across cosmic time. This continuity is reassuring, in the sense that it confirms the universality of the physical laws, but is also somewhat surprising given the differences in conditions, and it raises the question of how robust the structure formation process is to changes in the environment. One way to explore this question is to compare the statistical properties of the hidden web with those of the local web. Clustering statistics, which measure how galaxies are distributed in space, can quantify the degree of structure and the scale of the filaments and voids. If the clustering statistics of high redshift galaxies match the predictions of simulations based on the standard cosmological model, it would confirm that the model is correct even at early times. If they do not match, it would indicate that something in the model needs to be adjusted, perhaps the initial conditions, perhaps the physics of galaxy formation, perhaps the properties of dark matter or dark energy. Early results from James Webb suggest that the clustering of high redshift galaxies is broadly consistent with expectations. But there are hints of differences in the details, such as a possible enhancement in the number of close pairs of galaxies or an excess of galaxies in certain types of environments. These hints are still being investigated, and it will take more data and more careful analysis to determine whether they represent real deviations from the model or simply reflect the statistical uncertainties inherent in small samples. Another way to compare the hidden web with the local web is to look at the properties of individual galaxies and how they depend on their environment. In the local universe, it is well established that galaxies in different environments have different properties. Galaxies in dense clusters tend to be elliptical, with old stellar populations and little ongoing star formation, while galaxies in filaments or voids tend to be spirals, with younger stars and active star formation. This environmental dependence is thought to arise from the interactions between galaxies and their surroundings. Ram pressure stripping of gas in dense environments, tidal interactions during close encounters, the supply of fresh gas from the intergalactic medium in low-density regions. If similar environmental effects operate in the early universe, then galaxies in the dense nodes of the hidden web should exhibit different properties from galaxies in the filaments or in relatively isolated regions, and observing these differences could provide insights into the processes that shape galaxy evolution. Preliminary studies of high redshift galaxies observed by James Webb have found evidence of environmental effects, though the picture is still incomplete. Galaxies in overdense regions, areas of the sky where the density of galaxies is higher than average, tend to be more massive and have higher star formation rates than galaxies in less dense regions, consistent with the idea that dense environments provide more material for galaxy growth. But there are also examples of massive, star-forming galaxies in relatively isolated regions, suggesting that environment is not the only factor determining galaxy properties, and that intrinsic differences between galaxies, perhaps related to the properties of their dark matter halos or the initial conditions of their formation, also play an important role. Disentangling these effects requires large samples of galaxies at a range of redshifts and in a variety of environments, and the hidden web, with its extensive population of high redshift galaxies, provides an ideal laboratory for such studies. The hidden web also offers an opportunity to study the early stages of galaxy cluster formation, a process that is still not fully understood. Galaxy clusters are the most massive bound structures in the universe, containing thousands of galaxies and vast quantities of hot gas, all held together by the gravity of enormous dark matter halos. In the local universe, clusters are well-established, mature systems, the products of billions of years of growth and evolution. But at high redshifts, clusters are in their infancy, protoclusters, overdense regions where galaxies are beginning to congregate but have not yet settled into the deep potential well of a fully formed cluster. Observing protoclusters allows astronomers to study how clusters assemble, how galaxies within protoclusters differ from field galaxies, and how the cluster environment affects galaxy evolution from the earliest times. Several protoclusters have been identified in the deep fields observed by James Webb, recognized by the presence of multiple galaxies at the same redshift within a small region of the sky. These protoclusters, existing less than 1 billion years after the Big Bang, are among the earliest known examples of large-scale structure, and they provide a window onto the processes that will eventually lead to the formation of massive clusters in the later universe. By studying the properties of galaxies in these protoclusters, their masses, star formation rates, morphologies, and chemical compositions, astronomers can learn how the cluster environment influences galaxy evolution at early times, whether it accelerates star formation by providing a rich supply of gas, or suppresses it through interactions and feedback, or does both at different stages of the cluster's development. The discovery of protoclusters in the hidden web also has implications for the theory of biased galaxy formation. The idea that galaxies do not form uniformly throughout the universe, but preferentially in regions where the dark matter density is higher than average. This bias arises because higher density regions have stronger gravitational fields, which pull in more gas and allow galaxies to form more easily. As a result, galaxies are more clustered than the underlying dark matter, and the degree of clustering, the bias, depends on the properties of the galaxies, such as their mass and star formation rate. Massive galaxies, which form in the most massive dark matter halos, are expected to be more biased, more strongly clustered, than less massive galaxies. Observations of high redshift galaxies can measure this bias and compare it with predictions from simulations, providing a test of models of galaxy formation and a probe of the relationship between galaxies and dark matter. Early measurements of the clustering of high redshift galaxies in the hidden web suggest that they are indeed strongly biased, more so than galaxies at later times, indicating that they reside in the most massive dark matter halos available at their epoch. This is consistent with the expectation that the first galaxies form in the rare, high-density peaks of the initial fluctuation field, the regions that collapse first and most completely. As time progresses and more of the universe collapses into structures, galaxies form in less extreme environments, and the bias decreases. The hidden web, by revealing the galaxies in the earliest stages of this process, allows astronomers to test this picture and to refine models of how galaxies and dark matter are related across cosmic time. The hidden web also intersects with the study of the first stars and the first black holes, two of the most important and least understood phenomena in the early universe. The first stars, known as population 3 stars, are thought to have been very different from stars today. They formed from primordial gas containing only hydrogen and helium, with no heavier elements, and theoretical models suggest they were extremely massive, perhaps tens or even hundreds of times the mass of the Sun, and very short-lived, exploding as supernovae after only a few million years. These explosions would have enriched the surrounding gas with the first heavy elements, seeding the formation of subsequent generations of stars and eventually leading to the chemically complex universe we see today. But population 3 stars have never been directly observed because they are extremely rare and faint, and they exist at such high redshifts that even their explosions are difficult to detect with current instruments. James Webb, with its sensitivity to extremely faint and distant sources, has the potential to detect the signatures of population 3 stars, either by observing the galaxies that host them or by detecting the supernovae that end their lives. Some of the galaxies in the hidden web, particularly the smallest and least massive ones, may be dominated by population 3 stars or their immediate descendants, and their spectra may reveal the characteristic features of metal-free or extremely metal-poor stellar populations. If such galaxies can be identified and studied, they would provide invaluable information about the properties of the first stars and the role they played in shaping the early universe. Similarly, the first black holes, which are thought to be the seeds of the supermassive black holes that reside in the centers of galaxies today, are a subject of intense interest and considerable mystery. Supermassive black holes, with masses of millions or billions of times the mass of the Sun, are observed in galaxies at all redshifts, including at redshifts greater than 6, corresponding to times less than 1 billion years after the Big Bang. How these black holes grew so massive so quickly is not well understood, since the standard mechanisms for black hole growth, accretion of gas and mergers with other black holes, seem too slow to produce billion solar mass black holes in the time available. Various solutions have been proposed, including the formation of intermediate mass black hole seeds directly from the collapse of massive gas clouds, or episodes of super Eddington accretion in which black holes grow much faster than the standard limit, or the existence of massive population 3 stars that collapse into black holes without exploding as supernovae, providing more massive seeds than expected. The hidden web, with its population of early galaxies, may contain examples of these first black holes in various stages of growth, and observations of their host galaxies can constrain models of black hole formation and growth. Some of the brightest galaxies in the hidden web are likely powered in part by active galactic nuclei, the emission from gas accreting on as supermassive black holes. And studying these objects can reveal how common black holes are at high redshifts, how massive they are, and how they interact with their host galaxies. The relationship between black hole mass and galaxy mass, which is well established in the local universe, and suggests a deep connection between black hole growth and galaxy evolution, can be tested at early times by measuring the properties of both the black holes and their hosts in the hidden web, providing clues to how this relationship arose. Beyond galaxies and black holes, the hidden web also has implications for the study of dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy is usually studied through observations of distant supernovae, the cosmic microwave background, and a large-scale distribution of galaxies, all of which constrain its properties and its effects on cosmic evolution. The hidden web, by extending the map of large-scale structure to higher redshifts, provides additional data that can be used to test models of dark energy and to search for evidence of its evolution over time. If dark energy was significantly different in the early universe than it is today, that would affect the rate of structure formation and could leave detectable signatures in the distribution and properties of galaxies in the hidden web. Comparing the observed structure with predictions from models with different dark energy properties could help to distinguish between a true cosmological constant, which does not vary over time, and more exotic forms of dark energy that evolve, such as quintessence or modifications to general relativity. The discovery of the hidden web has also renewed interest in the question of whether the universe is larger than the observable universe, whether it extends beyond the horizon defined by the finite speed of light and the finite age of the universe. The observable universe, by definition, is limited to regions from which light has had time to reach us since the Big Bang, a distance of roughly 93 billion light-years in all directions, accounting for the expansion of space. But there is no reason to believe that the universe stops at this horizon. It almost certainly extends beyond it, perhaps infinitely, containing galaxies, stars, and structures that are simply too far away for their light to have reached us yet. The hidden web, though within the observable universe, was previously beyond the reach of our instruments, hidden in a different sense, and its discovery is a reminder that the boundary of the known universe is not fixed by physics but by technology, and that as our instruments improve, we can push that boundary closer to the true edge of observability. If the universe is infinite or even just much larger than the observable portion, then the hidden web we have discovered is only a tiny fraction of the total structure, a local sample of a pattern that extends far beyond our ability to observe. This thought is both humbling and awe-inspiring, a recognition that our place in the cosmos is even smaller than we imagined, that the observable universe, vast as it is, may be merely a minuscule patch in an incomprehensibly larger whole. But it is also empowering, in the sense that every advance in our observational capabilities allows us to see more of that whole, to extend the map of reality further, and to deepen our understanding of the structure and nature of existence. The hidden web also serves as a case study in the philosophy of science, illustrating how scientific knowledge is constructed and how it evolves in response to new data. The known universe, as it existed before James Webb, was a synthesis of observations accumulated over decades, interpreted through the framework of physical theories and cosmological models that have been tested and refined through countless studies. It was a coherent, self-consistent picture supported by a wide range of evidence, and it represented the best understanding of the cosmos that the scientific community had achieved. But it was never claimed to be complete or final. Science is inherently provisional, always open to revision in light of new evidence. The hidden web, by revealing structures and populations that were not fully accounted for in the previous picture, has prompted a re-evaluation of that picture, not a rejection of it, but a refinement, an expansion, an adjustment to incorporate the new data. This process of refinement is central to the scientific method. Theories are judged not by their perfection, but by their ability to explain observations and make testable predictions. And when new observations arise that the theory does not explain, the theory is modified to accommodate them. Sometimes the modifications are minor, tweaks to parameters or the addition of new details. Sometimes they are major, requiring fundamental changes to the underlying assumptions or the introduction of new physics. The hidden web, depending on how the data develops, may require modifications of either kind, and the ongoing effort to integrate it into the broader framework of cosmology is an example of how science progresses through the interplay of observation and theory. There's also a human dimension to the discovery of the hidden web, a story of the scientists and engineers who made it possible. The James Webb Space Telescope is the product of decades of planning, design, and construction, involving thousands of people from dozens of countries, working across multiple space agencies, universities, and research institutions. Its development was fraught with challenges, technical difficulties, budget overruns, delays, and there were moments when the project seemed in jeopardy. But the commitment to the science, the belief that the discoveries it would enable justified the effort and expense, kept the project moving forward. And when the telescope finally launched and began returning data, it exceeded even the optimistic expectations of its designers. The scientists who are now analyzing the data from James Webb, identifying the galaxies of the hidden web, and working to understand their properties and significance, are the beneficiaries of that long effort. They are also the inheritors of a tradition that stretches back to the earliest astronomers, who looked up at the night sky and wondered about the nature of the stars, the motion of the planets, and the structure of the cosmos. Each generation has built on the work of the previous, developing new instruments, new techniques, new theories, and passing them on to the next generation to be refined and extended. The discovery of the hidden web is a continuation of that tradition, a milestone in the ongoing human endeavor to understand the universe, and it is made possible by the cumulative effort of countless individuals, most of whose names will never be widely known, but whose contributions are nonetheless essential. In a broader sense, the hidden web is a reflection of humanity's drive to explore and to know, to push beyond the boundaries of the familiar, and to seek out what lies beyond. This drive is not unique to astronomy. It manifests in every field of human endeavor, from the exploration of the Earth's oceans and continents to the probing of the microscopic world of atoms and cells to the investigation of the nature of consciousness and the origins of life. But astronomy has a special character in that it deals with the largest scales and the deepest times, with questions that touch on the origin and fate of everything that exists. The hidden web, as a structure that spans billions of light years and billions of years of cosmic history, connects us to the universe in a profound way, revealing our place within it and the processes that shape the conditions for our existence. It is worth pausing to consider the sheer scale of what has been revealed. A single galaxy, like the Milky Way, contains hundreds of billions of stars, each one a sun, many of them likely accompanied by planets. The hidden web contains millions of galaxies, perhaps more, each with its own population of stars and possibly planets, distributed across a volume of space so vast that light takes billions of years to cross it. The number of stars in the hidden web is beyond human comprehension, a number so large that it becomes abstract, meaningless in any intuitive sense. And yet, each of those stars is a real object, a ball of plasma fusing hydrogen into helium, emitting light and heat, evolving over millions or billions of years, eventually exhausting its fuel and dying, perhaps leaving behind a remnant, a white dwarf, a neutron star, a black hole, or dispersing its material back into space to be recycled into new generations of stars. The processes that govern the life cycles of stars, the chemistry they produce, the structures they inhabit, are the same throughout the hidden web and throughout the universe, a testament to the universality of physical law. This universality is one of the most profound insights of modern science, the recognition that the laws of physics are the same everywhere, in every galaxy, at every epoch throughout the cosmos. The life in the galaxies and the hidden web analyzed through spectroscopy, reveals the same spectral lines, the fingerprints of hydrogen, helium, carbon, oxygen, and other elements that we observe in stars and gas clouds in our own galaxy. The gravitational dynamics that govern the motion of galaxies in clusters, the formation of filaments, the collapse of dark matter halos, are described by the same equations that describe the fall of an apple or the orbit of the moon. The nuclear reactions that power stars, fusing light elements into heavier ones and releasing energy in the process, operate according to the same principles in the hidden web as they do in the sun. This universality allows us to interpret observations of distant galaxies, to infer their properties, to model their evolution, and to draw conclusions about the nature of the universe. Even though we can never visit them, never probe them directly, never examine them with anything other than the light they emit. The hidden web, then, is not just a collection of distant objects, but a laboratory for testing our understanding of the universe, a place where physical laws and cosmological models can be confronted with observation. Every galaxy in the hidden web is a test case, a data point that either confirms or challenges our theories and the aggregate properties of the web as a whole. Its structure, its density, its evolution provide powerful constraints on the models we use to describe cosmic history. The fact that the hidden web exists, that it has the properties it does, tells us something deep about the nature of the universe, about the initial conditions from which it emerged, about the forces and processes that have shaped it, and about the ultimate fate that awaits it. And this brings us to one of the most profound questions raised by the hidden web. What does it tell us about the future of the universe, about the destiny of cosmic structure and the galaxies that inhabit it? The universe is expanding, and that expansion is accelerating, driven by dark energy. In the far future, billions of years from now, the acceleration will carry distant galaxies beyond the horizon, redshifting their light so severely that they will fade from view, eventually becoming undetectable no matter how sensitive our instruments. The observable universe will shrink, in a sense, containing fewer and fewer galaxies as they are carried beyond the reach of observation. Eventually, in the unimaginably distant future, the only galaxies remaining visible will be those in our local gravitational neighborhood, the members of our local group, which are bound together tightly enough that the expansion of space cannot pull them apart. The rest of the universe, including the hidden web and all the other structures we see today, will have receded beyond the horizon, invisible, unreachable, effectively existing in a separate domain of space-time. This long-term future, though based on our current understanding of dark energy and cosmic expansion, is highly uncertain. Dark energy, as mentioned earlier, is not well understood, and if its properties change over time, the future evolution of the universe could be very different from what current models predict. If dark energy weakens, the expansion could decelerate, perhaps even reverse, leading to a big crunch in which all matter eventually collapses back into a singularity. If dark energy strengthens, the acceleration could become so extreme that it tears apart not only the cosmic web, but eventually galaxies, stars, planets, and even atoms, a scenario sometimes called the Big Rip. Or dark energy could remain constant, leading to an ever-expanding, ever-cooling universe in which stars eventually exhaust their fuel, black holes evaporate through Hawking radiation, and the cosmos approaches a state of maximum entropy, a heat death in which no complex structures remain and no processes occur. The hidden web, observed at a time when the universe was young and structure was still forming, provides a contrast to these long-term scenarios. It shows us a universe full of activity, of galaxies forming and evolving, of gas collapsing and igniting into stars, of energy and matter in constant motion and transformation. The structures it reveals are not eternal, but are products of a specific epoch in cosmic history, a time when the density of the universe was high enough and the expansion slow enough that gravity could pull matter together into coherent systems. In the far future, those conditions will no longer hold, and the cosmic web will gradually dissolve, its filaments stretching and thinning, its galaxies growing more isolated, its activity winding down as the universe expands and cools. But that future is trillions of years away, far beyond a lifetime of any current stars, far beyond the timescales relevant to human existence or to the existence of any life that might inhabit the universe today. For now, the hidden web is a vibrant, dynamic structure, and its study offers insights into the processes that have shaped the cosmos and that continue to operate in the galaxies and structures we see around us. It is a reminder that the universe is not static, not a fixed backdrop against which events unfold, but a dynamic, evolving entity, constantly changing, constantly revealing new aspects of itself to those who look closely enough. The discovery of the hidden web also invites reflection on the nature of discovery itself, on what it means to find something that was always there but never seen. In one sense, the hidden web is not new. It has existed for more than 13 billion years, since the first galaxies that compose it began to form. It was part of the universe long before humans evolved, long before the Earth formed, long before the sun ignited. It has been radiating light into space all that time, light that has been traveling across the cosmos, carrying information about those galaxies, waiting for an observer with the right instruments to detect it. In another sense, the hidden web is new, a recent addition to human knowledge, a structure that entered our awareness only with the deployment of James Webb and the analysis of its data. The galaxies themselves have not changed, but our knowledge of them has, and that change in knowledge is itself a significant event, one that alters how we think about the universe and our place within it. This duality, the objective existence of the hidden web and its subjective newness to human understanding, highlights the relationship between the universe as it is and the universe as we know it. The two are not the same. Our knowledge is always incomplete, always lagging behind reality, always shaped by the tools and perspectives we bring to bear. But through the process of observation, measurement, and analysis, we gradually bring our knowledge into closer alignment with reality, refining our maps, correcting our errors, expanding our understanding. The discovery of the hidden web is a step in that process, a moment when the gap between the known and the actual narrowed, if only slightly, and a portion of the cosmos that was hidden became visible. There is also something deeply human in the act of naming, in calling this newfound structure the hidden web, and in describing its galaxies, filaments, and voids with the same language we use for structures in the local universe. Names and categories are tools we use to organize and communicate knowledge, to make sense of the overwhelming complexity of the world. By naming the hidden web, by classifying its components, by comparing it to structures we already know, we make it comprehensible, we integrate it into our existing framework of understanding. But we must also remain aware that names and categories are human constructs, that they do not capture the full reality of the things they describe, and that the universe itself does not divide neatly into the boxes we create for it. The hidden web is a useful term, a shorthand for a complex set of observations and interpretations, but it is not the universe as it is. It is the universe as we currently understand it, filtered through our instruments and our theories. The galaxies of the hidden web emit light in many wavelengths, from ultraviolet to visible to infrared to radio, and each wavelength tells a different story. The ultraviolet light comes from hot, young stars, the visible light from older stellar populations, the infrared from dust warmed by star formation or from starlight redshifted by cosmic expansion, the radio from synchrotron emission by relativistic particles or from the glow of cold hydrogen gas. James Webb observes primarily in the infrared, capturing the light that has been redshifted by billions of years of expansion, and this is why I can see the hidden web at all. But a complete understanding of these galaxies will require observations at other wavelengths as well, using other telescopes, each adding a piece to the puzzle. The Atacama Large Millimeter/Submillimeter Array, ALMA, for example, observes in millimeter and submillimeter wavelengths, detecting the emission from cold dust and molecular gas, the raw material for star formation. The Chandra X-ray Observatory and the Newton satellite observe in X-rays, detecting the hot gas of galaxy clusters and the accretion disks of black holes. Future radio telescopes, such as the Square Kilometer Array, will observe the distribution of neutral hydrogen, tracing the gas from which galaxies form and the intergalactic medium through which they interact. Together, these multi-wavelength observations will build a comprehensive picture of the hidden web, revealing not just the locations and distances of its galaxies, but their physical properties, their compositions, their dynamics, their interactions with their environment, and their evolutionary histories. This multi-wavelength approach is essential in modern astronomy, since no single telescope or wavelength can capture the full complexity of cosmic phenomena. The hidden web, like all structures in the universe, is best understood not through a single snapshot, but through a composite image, assembled from many observations at many wavelengths, each contributing a unique perspective. The process of assembling this composite image is ongoing, and it will take years, likely decades, to complete. James Webb has revealed the existence of the hidden web and provided the first detailed observations of its galaxies. But much work remains to be done. Follow-up observations with other telescopes are needed to measure the properties of these galaxies across the electromagnetic spectrum. Spectroscopy is needed to determine precise redshifts and to analyze the chemical compositions of the galaxy's stars and gas. Imaging at high angular resolution is needed to study the internal structure of the galaxies, to see whether they have disks, bulges, spiral arms, or other features. Gravitational lensing studies are needed to map the distribution of dark matter in and around the hidden web. And simulations are needed to interpret all of this data, to connect the observations to theoretical models, and to test hypotheses about how the hidden web formed and how it fits into the broader picture of cosmic structure. This work is not being done in isolation, but is part of a larger international effort to understand the universe. Astronomers from around the world, working at observatories and universities and research centers on every continent, are collaborating to analyze the data from James Webb and other telescopes, sharing their findings, debating interpretations, and building a collective understanding of the cosmos. The discovery of the hidden web is the result of this collaboration, and its ongoing study will continue to be a collaborative effort, drawing on expertise from many fields: observational astronomy, theoretical physics, computer science, statistics, instrument design, and involving scientists at all stages of their careers, from students working on their first research projects to senior researchers with decades of experience. The human dimension of this work is easy to overlook, especially when the focus is on the science itself, on the galaxies and the models and the implications for cosmology. But behind every observation, every analysis, every paper published, there are people who spend long nights at telescopes, who write code to process data, who run simulations on supercomputers, who teach students, who write proposals for funding, who give talks at conferences, who debate ideas with colleagues, who balance the demands of research with the demands of life. The discovery of the hidden web is a product of their collective effort, and it is a testament to the power of human curiosity and collaboration, to the ability of people to work together across boundaries, national, linguistic, cultural, toward a common goal, the pursuit of knowledge. In this sense, the hidden web is not just a structure in the universe, but a structure in human understanding, a new element in the ever-growing edifice of scientific knowledge. Each discovery adds to this edifice. Each new observation provides a new piece that must be fitted into the existing framework, sometimes requiring adjustments or expansions to accommodate it. The edifice is never complete. It is always a work in progress, always being revised and refined, always growing as new data becomes available. The hidden web is the latest addition, a significant one, and it will take its place alongside other great discoveries in the history of astronomy. The expansion of the universe, the cosmic microwave background, dark matter, dark energy, exoplanets, as a milestone in the ongoing effort to understand the cosmos. As the study of the hidden web continues, it is likely that new questions will emerge, questions that cannot yet be anticipated because they depend on observations not yet made or analyses not yet performed. This is the nature of scientific research. Every answer leads to new questions. Every discovery opens new avenues of inquiry, and the frontier of knowledge is always advancing, always receding, always revealing new terrain to be explored. The hidden web, which began as a collection of unexpected galaxies in the deep infrared images of James Webb, has already raised questions about galaxy formation, cosmic structure, dark matter, and the timeline of the universe. As more data becomes available, as more detailed observations are made, as more sophisticated models are developed, those questions will be refined and new ones will be added, and the picture of the hidden web will become richer and more complex, approaching but never quite reaching a complete understanding. This open-endedness is not a flaw, but a feature of science, a reflection of the fact that the universe is immensely complex and that our knowledge, however extensive, is always finite and always provisional. The discovery of the hidden web is a reminder of this, a demonstration that no matter how much we learn, there's always more to discover, always deeper questions to ask, always further layers of reality waiting to be revealed. It is a humbling thought, but also an inspiring one, an invitation to continue the journey, to keep looking, keep questioning, keep exploring, and to see what else the universe has to show us. The hidden web, then, is not merely a set of galaxies or a region of space or a pattern of structure. It is a window onto the early universe, a laboratory for testing cosmological models, a challenge to existing theories, a catalyst for new research, and a symbol of the open-ended nature of scientific inquiry. It is a reminder that the universe is larger and more complex than we can fully comprehend, that our maps are always incomplete, and that the boundary between the known and the unknown is not fixed, but is constantly shifting as we develop new tools and new insights. It is a testament to the power of technology, the dedication of scientists, and the enduring human drive to understand the cosmos. And it is, above all, a continuation of the story that began when the first humans looked up at the night sky and wondered what was out there, a story that has no end, only an ever-expanding horizon. As James Webb continues to observe, as more data is gathered, as the hidden web is mapped in ever greater detail, the story will continue to unfold, revealing new chapters, new surprises, new insights. The galaxies that make up the web will be studied individually and collectively, their properties measured, their histories reconstructed, their roles in the cosmic web understood. The filaments that connect them will be traced, their densities measured, their dynamics modeled. The voids between them will be explored, their emptiness quantified, their influence on the surrounding structure assessed. And all of this information will be integrated into a larger picture, a picture of how the universe has evolved from a hot, dense, nearly uniform state shortly after the Big Bang to the rich, complex, structured cosmos we see today, a cosmos in which the hidden web is but one piece, though a significant one, of a far grander tapestry. That tapestry extends in all directions, across billions of light years, and back in time nearly to the beginning. It includes structures we have known for decades, like the Virgo cluster and the Coma cluster, and structures only recently discovered, like the hidden web. It includes galaxies like our own Milky Way, with its hundreds of billions of stars, its spiral arms, its central black hole, and countless other galaxies, each unique, each with its own history. It includes the intergalactic medium, the dark matter that shapes the web, the dark energy that drives the expansion, and the cosmic microwave background that echoes from the distant past. It is a tapestry woven from gravity and quantum mechanics, from the physics of particles and the dynamics of space-time, from the initial conditions set by inflation and the long, slow process of structure formation that has unfolded over 13.8 billion years. And it is a tapestry that we are only beginning to see in its full complexity, thanks to instruments like James Webb and the dedicated efforts of astronomers around the world. The hidden web, discovered in the infrared light detected by one of the most advanced telescopes ever built, is a new thread in this tapestry, a newly visible strand that connects to and extends the patterns we already knew. It is a thread that reaches back to the first billion years of cosmic history, to an epoch when the universe was young and stars were just beginning to form, and it carries forward to the present, influencing the structure we see today and shaping the evolution of galaxies over billions of years. It is a thread that connects us here on Earth to the distant past and the distant reaches of space, reminding us that we are part of the universe, that our existence is a consequence of the same processes that form the hidden web and all the other structures it contains. In contemplating the hidden web, we are contemplating not just distant galaxies, but the nature of existence itself, the fact that the universe is not a static, unchanging backdrop, but a dynamic, evolving entity, constantly creating new structures, new patterns, new possibilities. We are contemplating the fact that reality extends far beyond what we can see, that the observable universe is only a fraction of the whole, and that even within the observable universe, vast regions remain hidden, waiting to be explored. We are contemplating the power of human ingenuity, the ability to build instruments that can see across billions of light years and billions of years, that can capture light so faint it has been traveling since the universe was a fraction of its current age, and that can transform that light into knowledge, into understanding, into a picture of the cosmos that is deeper and richer than any previous generation could have imagined. The hidden web is a frontier, a boundary between the known and the unknown, and like all frontiers, it invites exploration. It invites us to push further, to look deeper, to ask harder questions, to develop better tools, and to continue the quest for understanding that has driven astronomy since its inception. It invites us to confront our ignorance, to acknowledge how much we do not know, and to embrace the uncertainty and the mystery that come with exploring the unknown. It invites us to be humble in the face of the universe's complexity and ambitious in our efforts to comprehend it. And it invites us to recognize that the journey is as important as the destination, that the process of discovery, the act of looking and learning and understanding, is itself a valuable and meaningful endeavor, regardless of where it ultimately leads. As we continue to study the hidden web, as we map its galaxies, measure their properties, model their evolution, and integrate them into our broader understanding of cosmic history, we will be adding to the ever-growing body of human knowledge, expanding the frontier of the known, and pushing back the boundaries of the unknown. We will be contributing to a story that began long before any of us were born and that will continue long after we are gone. A story of the universe and our place within it. A story that is written not in words, but in observations, in measurements, in equations, in images captured by telescopes pointing at the farthest reaches of space and the deepest reaches of time. The hidden web is a new chapter in that story, and it is a chapter that is still being written, still unfolding, still revealing its secrets. And so we watch, and we wait, and we analyze, and we wonder as the data continues to accumulate, as the picture continues to sharpen, as the hidden web slowly emerges from the darkness, transformed from a region of unsurveyed space into a mapped and studied domain, integrated into our understanding of the cosmos. We watch as the galaxies within it are counted, cataloged, and characterized, as their connections and relationships are traced, as their histories are reconstructed, and as their implications for cosmology and galaxy formation are debated and explored. We watch as the boundary between the known and the unknown shifts, as new questions are posed, as new observations are planned, and as new instruments are designed to probe even deeper, to see even further, to reveal even more of the vast, intricate, and beautiful structure of the universe in which we live. The hidden web is not the endpoint of this journey, but a waypoint, a marker along the path, a sign that there is still so much to discover, so much to understand, so much to marvel at. It is a reminder that the universe is full of surprises, that no matter how much we learn, there is always more waiting to be found, and that the quest for knowledge is unending, a journey that stretches from the first moment we looked up at the stars to the far future, when perhaps our descendants, equipped with instruments we can scarcely imagine, will look back at our time and marvel at how little we knew, how much was still hidden from us, and how far they have come since then. Until that time, we continue to observe, to measure, to analyze, and to wonder, guided by the light that reaches us from the distant reaches of space and time, light that carries within it the history of the universe and the promise of discoveries yet to come.